All right, welcome to class today. And thank you for being here. Today we're going to look at a couple of topics. We're going to look at sampling distribution. We're also going to look at central limit theorem. And then we're going to look at normal approximation of binomial distribution, right? And so we're going to look at all that today. So I want to begin to explain by explaining what sampling distribution is. And then when I explain that, we're going to look at some examples so we all understand the concept. And then we also will move on and look at central limit theory. So what is the theory behind central sampling distribution? Now, if you remember the first few weeks, right, when we began, in fact, week one, we talked about population, right? And then we talked about sample. We said population is the entire outcomes, objects, or people that you want to investigate or you want to research. And then we said sample is basically a part of that population. So if I want to find out about a population, sometimes it's not easy. For example, if I want to find out about all the students at PCC, right? You guys have about 30-something thousand people. I want to do a research on you, it's almost impossible to get 30,000 people to interview. So an easy way or an easier way is to do a sample. And the sample means I'll pull a few of you, right? Maybe 1,000, maybe 5,000 of you, and then I'll sample you. And whatever you guys tell or ladies tell me will now be a representation of what the population is, right? Now, if you remember, we also said that there are different ways that we sample people. We said there was one was cluster, one was convenience, one is KTH. So then we had random sampling, we had convenience, and then we also had a couple of other ones, right? And the reason why we said that some of them were good, that's 35, right? We said some of them were good, some were not so good. Because when you sample a group, you want to get a result that really looks like a group, right? If I sample you guys and ladies, and you tell me you like oranges, that means that I should be able to look at the whole PCC students and say that most of them like oranges because the sample that I got told me this, right? So that's what sampling is. Now, but most times, what we sample is different from what the population is. There is a gap between what the real value is and what we are saying. That difference is called standard error, which we'll talk about later. The difference between what the population sample is and what the sample we get is. Now, but there's some core concepts about sampling distribution I want to explain. What sampling distribution is saying, and this is what I want to look at, the first one here, is saying that the average of the population, or the population mean, is equal to all the samples taken, and you find the sum of the average of those samples. You get the same result. So let me explain it again. What he's saying is, let's say, for example, right, the average age of students at PCC is 34 years. Right? Let's say that's the average, population average. What this theory is saying is that if you take the sample, all the samples, right? If you take all the samples, the average of all those samples will give you what? 34 years. That's what the rule says, right? Or that's what the property says. So the sum of all your sample means will give you the same result as your population mean. That's interesting, right? That's an interesting concept. So we're going to check this out to see if it's true with a small experiment. The second theory or property says that the standard deviation, right, of your sample means, when you have your sample means, the standard deviation of that, right, is actually equal to the standard deviation of your population divided by the square root of n. And those are two big concepts. I want to explain those concepts, show you an example of that. By the time you understand this concept, you'll be able to apply it in anything we're solving in the class, right? So in order to do that, right, let's go into our Excel and try that and see if that is true, right? So what I'm going to do here is I'm going to stop sharing my Word document, and then I'm going to go into Excel, and we're going to try and test this out, right? So let's go to Excel. So what we're going to do right now is to test and see if that theory holds true, right? And so we're going to come up with a population. So look at this example. It says that imagine you had 4 pieces of paper, and in each paper, you write a name, fold it, and drop it in a box, right? Paper 1 has 1 on the paper, right? So you have 4 papers, right? So let's do that. Let me show you that. So you have 4 papers, right? And so when you have these 4 papers, on one of the paper you put 1, on the other one you put 3, the other one you put 5, the other one you put 7. You squeeze them all together, all 4 of them, right? And you drop it into a cup or a plate or anything, right? And you squish them, right? And now the question is, list all possible samples of size n is equal to 2 and calculate the mean of each, right? What are all the possible selections if you choose 2 only? If you're going to choose only 2 papers out of this container, right? What are all the possible selections that you can? Who wants to help me with that? With all the possible numbers you can select. So you pick a number, you drop it, and you pick it again, right? What are all the possible numbers you can pick? Because this is the population, right? 1, 3, 5, and 7. 1, 3, 5, and 7. Anyone? Reese, what are all the possible numbers we can select here?
Like just pick like 2?
Yes, but you pick one at a time. So you pick a number, you drop it, you pick it again. What are all the possible numbers you can pick?
I mean, you could pick 1 and 3 and like 1 and 5 and 1 and 7.
Good. You can pick, you're right. You can pick 1 and 1. You can pick 1 and 3. So let's put it in order, right? We'll put it in order so that it makes more sense. So we can pick 1 in 5, right? And then you can pick 1 and 7, right? And then we can go to the next one, which is 3, right? Then we can say you can pick, you have 4 instances, right? You can pick 3. So you can pick 3 and 1, right? 3 and 3, 3 and 5, and 3 and 7, right? How about 5s, right? You can do that in 4 options too. You can pick 5 and 1, 5 and 3, 5 and 5, 5 and 7. Number 7, right? You can pick 4 kinds of 7, right? 7 and 1, 7 and 3, 7 and 5, 7 and 7. All right, so looking at this, right? Can anyone tell me any number we've left out? Any combination we've left out here? So this is all the combination, right? So what the theory says is that if we find the mean of this, the average of this, and then we find the average of all our results, our answer would be the same. Now remember, right? These are all the samples. This is one sample, this is another sample, this is another sample. So it means that maybe if Reese was picking, she'll pick 1 and 1. If Samuel was picking, Samuel will probably pick 1 and 3. if Yahir was picking, he'll pick 1 and 5, right? So we're going to test this theory. So we're going to say, let's find the average of this. So the average of this one is 1, right? And so we find the average of all of them. This is what is very scary. You know how you watch TV, right? Or sometimes you read the news and you're looking at poll results and say, okay, the sample shows that 40% of Americans love chicken, right? This is why some of the times you have to look very well at those samples, because the results can be amazingly wrong. Because look at this, right? Reese did her own survey, her own sample, and she said her answer was 1. But look at the real result. This is the population, right? These are all the 4 numbers that are there. So look at the population. It's equal to average. Average is 4. This is why sometimes sampling can be very wrong. Because if Reese did this, she got 1. Samuel did this, he got 2. Yahiro did it, got 3. Each of you got it wrong because the average was actually what? 4. Right? So the theory says that if you find the average of all these numbers, you will get the same thing as 4. So let's test it out. So we'll now say this is equal to the average of all these values gives us what? 4. This is very important in sampling. It means that the sample or the mean of sample means is equal to what? The population mean. So the mean of your sampling distribution will always be equal to what? The population mean. Which means if I collect the sample, all the possible samples of a population, at the end of the day, my result will be the same as what? Anyone? Anyone? If I add up all, if I get my sample means, right, and I find the average of my sample mean, right, it'll be equal to what? Thank you, population mean. That's the first theory. The second theory now says that the standard deviation of your sample means is equal to the population standard deviation of this divided by the square root of your sample mean. That's the second rule, right? This is rule 1. So let's do rule 2. Rule 2 is saying that the standard deviation of your sample mean is equal to standard deviation over what? The square root of n. This is going to be a very important concept because this means standard error. This is the difference between your population mean and your sample mean. So this is very important. So first of all, let's prove to see if this theory is correct, right? To prove that, we're going to say, okay, for this first one, the formula will be equal to, all right, let's come here. It will be equal to the standard deviation of all these values. And our answer here is what? 1.58. Right? Now let's find out if it's the same here. They're telling us that this is equal to, look at what it says here. So if I do the standard deviation of these values and I divide it by the square root of our sample size, I'll get the same answer. See? So we have proven that these two theories hold true. That the sample, the average of the sample means is equal to the population mean. That's 1. 2, that the standard deviation of the sample means is equal to the standard deviation, population standard deviation over what? The square root of what? N. Any questions? This is going to be very useful as we go on, but this is just kind of proving our theory, that our theory is correct. Now, when we're solving questions involving sampling distribution, we tend to solve it in form of a normal distribution, right? So let's take this sample means and see if we can do that. So I'm going to go here and do X. I'm going to go here and do F, and then I'm going to do probability of X, right? In this scenario, basically. So who can tell me, somebody help me out, what are the numbers here? Can someone tell me all the numbers that I hear from the smallest to the biggest number? Anyone? Samuel, what are all the numbers on the third column there?
Come again?
So I want you to tell me all the numbers in this column here.
The odd numbers?
All the numbers in that column.
1, 2, 3, 4, 5, 6, 7.
How many ones do we have there?
1,
How many twos?
2,
How many threes?
3,
How many fours?
4,
How many fives?
and 3.
You sure? Okay.
5s. Yeah, there's 3 5s.
We're going to find out if you're correct. How many six do we have?
1, 2, 2,
How many sevens?
and 1, 7.
All right. We can tell if you're correct, but if we do the sum of this, right, it should give us, if we do the sum of this, we add this up, that will give us 16, right? And if we do the sum of this, that will also give us, this should also give us 16. So we know we're correct. Oh, 64 divided by 4. Yeah. So it's 16. I should have done some, sorry, my bad. I should do count, right? If I do count and I count this, I'm going to give it 16. So we know we're fine. So if we're looking for the probability of X, right, we will say this is equal to, remember, right? So this is 1 divided by 16. So you're asking, what is it trying to do? What I'm trying to do here is to show you that this question, it's going to be, when we're solving questions that have to do with sampling distribution, it usually falls into like a normal distribution, right? So we can do that. We can actually say, take these values and say, let's go and run it as in the form of a data set. So you can see that this is an example of a normal distribution, right? See how it falls. You can see that this is a normal distribution. You can see the graph, right? It's normal distribution, right? Remember, we said that for a normal distribution, right, it has to be symmetric. So if we look at this last one, this one and this one, you can see that it's symmetric about the mean, right? And so what we have here is a clear example of normal distribution, right? All right, and so that's kind of if someone is asking you, why do we use that question why do we use normal distribution? Well, we use it because of that. It forms normal distribution. You can see that it forms normal distribution. All right. Any questions on that? If you are confused, there's a better one that I like to use sometimes in my class. This one, I like this one because this one basically tells you it doesn't leave you with any confusion. Straightforward, right? You can see the distribution. So what does that mean? It means that when you are solving questions involving sampling distribution, right, we usually use normal distribution because it basically is symmetric about the mean. Any questions? Okay.
Yeah, Professor, how'd you get PX again?
Oh, just the normal way we do it. So we just do your frequency, right? Divided by your total frequencies.
Oh, okay.
Yeah, so we'll just do that. Yeah, for that. Yeah. So remember probability distribution we did a couple of weeks ago. So obviously I would ask you for this. Everything I'm showing you right now, I'm not going to ask you in the exam. It's just to prove the theory, basically. Right? Because it's one thing for you to know it, right? How about understanding it? And so what I want you guys to do is to understand it and say, oh, okay, I know why that crazy teacher was saying that. This is why we're doing normal distribution, because it actually is symmetric, which we're seeing here, right? So remember we used this, right? It was the sample means that we use to create a sample normal distribution. Don't forget that as we move to the next question. All right. So now that we did that, right, let's now move on to the next area. And so the next thing we're going to do now is to look at, so I'm going to pull that up, is to look at central limit theorem, right? CLT. I always like to say BLT every time I see it. So what is central limit theorem? Central limit theorem and sampling distribution are just brothers and sisters, basically. Because it's a theorem, right, that describes the relationship between what? Sampling distribution of sample means and what? The population that the samples are taken from. So CLT, what CLT does is it looks at the relationship between the sampling distribution and the population from which the sampling distribution is pulled out from. So it's looking at all those numbers that we had and what? 1, 3, 5, and 7. The relationship between the two of them is called what? CLT. Right? And what CLT does is that it makes decisions, right, using the sample to tell us about the population. And it makes use of sampling distribution to do that as much as possible. Right? So I want you guys to see, the reason why we started with sampling distribution was because we're coming to CLT, and CLT is just how we use sampling distribution to solve questions that we have. Right? Now, let's look at the properties of CLT. Now, CLT has two key properties, right? One of the properties is for you to use CLT to solve questions, the difference between CLT and normal distribution is that with CLT, we tend to have a sample size. We pull the sample size to check. Remember that one we did a few minutes ago, we did N is 2, right? We did 2. And I had all of you select, I had Reese, and Reese said she'll pick 1 and 3 or 1 and 1, right? So N was 2. So in CLT, you usually select a number, right? Now, one of the key properties of CLT is that two. One is that you can only solve CLT if the number, which is N, is 30 or more, right? That's one of the rules. It has to be 30 or more. Unless the question says it's normally distributed. If the question says it's normally distributed, then that's fine. You solve it. But if it doesn't say that, then N has to be at least 30 for you to be able to solve it. That's the first rule. The second rule, you already know that one. It says it's divided into 2 parts or 3 parts. It says the sample means is equal to what? Population mean, which you all know that we already did that, right? We said population mean is equal to the mean of what? Sample means. Then it also says this. I'm not talking about variance because we hardly use variance, but also the standard deviation. It says the standard deviation of your sample means is the same as what? The standard deviation over what? The square root of N, right? It's very important to know these rules, and that's why I spent some time proving it, because we're going to be solving questions. We need to understand these rules as we do so, right? Now, look at what it says here. The standard deviation of the sampling distribution of the sample means is also known as what? the standard error. So this is also known as standard error. So if you have a question that asks you to find the standard error, it's the same thing as saying this, standard deviation over what? The square root of n, which n stands for what? The sample size. Any questions on that? All right. So all we've been doing so far here is just to prove theories, because we're going to solve a question right now, but I wanted to make sure that you understand the concepts behind it, right? That way, when we solve it, it makes more sense. If we just jump into the questions, you're going to be like, what's going on here, right? But if we're able to explain to you the whys behind it, then when we solve the questions, it makes way much sense for us, right? So let's start with an example, right? My kids. Let's go into Excel and start with the first one. So I'm going to go into Excel. I'm going to stop sharing. I'm going to go to my Excel. I hope you go there with me. That way we can start solving questions. So I always have to bend to be able to pull up my Excel. All right. Okay, so for this one, right, let me enlarge this so that you guys can see this very well. I need to find a better way of doing that. I can just do Zoom, right? All right, so let's work together on this one. Can you all see this clearly? All right. It says that the phone bills for residents in Alhambra has a mean of $63. $63. And the standard deviation of $11. And your sample size is what? 100. Right? And so we're told that a random supply of 100 cell phones are drawn from this population, and the mean of each sample is determined. It now says, find the mean and the standard error of the sample distribution. So I asked to find the mean of the sample distribution. And we're also asked to find the standard error of the sample distribution. All right. So who can help me solve the first one? What's the mean of the sample distribution? Anyone?
What was the question?
What is the mean of the sampling distribution?
$63.
Why?
Well, it says mean right there, doesn't it?
Yeah, this is mean. But here you ask to find the mean of the sampling distribution. So you say 63. That's asking you why is it 63?
Oh.
Anyone? Samuel, you want to explain your answer?
No, never mind. It's not right.
All right. So our answer here is 63, right? It's 63 because what I told you guys at the beginning of the class, right, the theory, and even on that CLT, I told you guys that the mean of the sample distribution is equal to what? The population mean. And here I told the population mean is 63. So if the population mean is 63, then the mean of the sample distribution will be what? 63, right? That was the first rule I gave you guys on that sampling distribution, and also the first rule I gave you guys on the CLT. right? The mean of the sampling distribution is always equal to the population mean. And the population mean is 63. The mean of the sampling distribution is what? 63. All right, next one. Who can tell me what the standard error of the sampling distribution will be? Anyone?
Is it 11? Am I wrong?
You are wrong.
What?
Nobody? Wow. This is going to be a long class. All right. I told you guys that the standard error is the same thing as the standard deviation of your sample mean. And I told you that the formula is what? Standard deviation over the square root of n. So for this one, the answer will be equal to the standard deviation over the square root, right, of 100. And so your answer here will be what? 1.1, right? And so that's your answer right there. So remember, we always have to interpret, right? So for CLT, right, the with sample size more than 30, the mean of the sampling distribution is 63, and the standard error is 1.10. That is your answer for question 1. All right, any questions on question 1? All right, let's try another one. So the second one, right? We're going to try the second one and see if we can get that one, right? Try to find an easier way than doing this. I feel like I'm dancing or something. All right, let's try another one. So this one says the training heart rates of 20 old athletes are what? Normally distributed. Okay, this is good. It's important to know that this is distributed with a mean of 135 beats per minute and a standard deviation of 18 beats per minute. The random samples of size 4 are drawn from the population, and the mean of each sample is determined. Find the mean and standard error of the mean of sampling distribution. So here, we're told that the population mean is given to us here as what? Gutierrez, what is our mean here? Population mean. Gutierrez, what is our population mean here?
It's gonna be 4.
So
No, my bad. It's gonna be 135. Sorry.
135 beats per minute. All right. And what's the standard deviation?
18.
18, thank you. All right, so we have that. And so our n is given as 4, right? All right, so the question is asking us to find the mean of the sampling distribution. And the second one is asking us to find the standard error of the sampling distribution. All right. So what is the answer for the mean? What's the mean of the sampling distribution?
135.
135, that's correct. Right? Okay. What is the standard error of the sampling distribution? Anyone?
I got 9. Is that right?
How did you do that?
So it's standard deviation 18 divided by the square root of n, which is 4.
Okay, divided by the square root of n, which is 4. And so that's correct. So we get 9. Right. And so for CLT, right? So we interpret the results, right? For CLT with a sample size of 4, but normally distributed. The mean of the sampling distribution is 135 bits per minute. The standard, thank you for doing that, is 9 bits per minute. All right. Any questions on this?
Professor, could you hover over the standard error? Okay, thank you.
You're welcome. All right. So what we've done in the first 2 assignments is basically to show you what, in essence, to show you what standard error is, how it's solved, to show you the relationship between the sample mean, the mean of sample mean or sample distribution, and how it's equal to the population mean, right? We're showing that relationship between those 2 values, right? So now that you got that, right, the next thing we're going to do now is let's solve a full question that is in CLT, right? We're going to solve a full CLT question, right? That covers all those bases, right? That's what our goal would be to do. Okay, so the one we have here, the person we have here, basically what it does is it's asking us to do a couple of things. And one of the things I want to tell you is when you're solving a question, if you remember how we did for normal distribution, right? If you remember what we did, usually we took the question, we found the X value, we converted that to Z values, and then we converted that to probability, right? And when we solve for CLT, it's just similar to how we solve with CLT, basically, or how we solve with normal distribution. There's only a slight difference. In normal distribution, you're asked to find the probability of a given individual or product or object in the whole scenario. For CLT, you are asked to select out of a sample set. So the difference is that n, because in CLT, they'll say a sample of 50, a sample of 100. And so you have to select based on that. That is the key difference between the 2 of them, right? And so remember, right, who can tell me the formula for Z when we are using normal distribution? Can any of you remember the formula for Z when we're doing normal distribution? We did this. This was last week, Wednesdays.
Is there going to be a normal inverse?
No, normal inverse is when you're finding the value of X.
Is it Z equals score minus mean divided by standard deviation?
So value minus mean, right? Whatever standard deviation, right? Now for CLT, it's similar, right? But remember, CLT is looking at the sample what? Distribution. So it's still going to be X minus mean. But who can tell me what's the formula for standard deviation of sampling distribution? What is the formula for standard deviation of sampling distribution? Come on, people, we just did this like a few minutes ago. If the question is given for sampling distribution, right? Standard deviation of a sampling distribution, what's the formula for that? All right. That will be standard deviation over the square root of n, right? And that's the formula for that. So that's the only difference between those two values, right? So when you're solving questions, that's the key difference between the two of them. So for all of them, it's going to be x minus mean, but for normal, it's standard deviation. For CLT, it's going to be standard error over what? I mean, standard deviation over square root of n, which is also known as a standard error. So that's the key difference between the two of them. All right. So now let's solve this question. We're told that the average time spent each day by each group is, and we're given the groups and the time they spent in each group, right? The average time. We're now told that the table shows length of time people spend driving each day. We're told that you randomly select 50 drivers. So here, n will be equal to 50 drivers. And then we're told that what is the probability that the mean time they spend each day is between 24.7 minutes and 25.5 minutes. Assume that the population standard deviation is 1.5. So we know that our standard deviation here is going to be 1.5, right? And so we know that 1.5 minutes. We also know that the average time, which is the mean, is given by 25 minutes here. So it's right here. So the average time is 25 minutes, right? So we have that. So now that we have this, right, we're asked to find the probability that the mean time spent each day is between 24.7 and 25.5. So what we have here is a normal question. Because n is more than 30, so we know that we can use CLT to solve it. We're told that the mean is 25 minutes, but we're also told that they spent the time of between 24.7 and 25.75. So this is 24.7 and 25.5. So what they're asking us is to find the probability of selecting this. All right? But these are for X values. So we know that for Z values, we know that this is 0. So we know, right, from what we've done before, we know that when you have two values and looking for the two values, you have to find the value of this one, find the values of this one, then subtract B from A. That will give you this space, right? And so to do that, we're going to say, all right, the X values, there are two. The first one is 24.7 minutes. The second one is 25.5. So we know that. The next one is to find our Z value. Now, we know that the formula to find our Z value is X minus mean over standard error. And we can actually solve this straightforward if we want to do that. But it might take us a little while. So the easiest way to solve this problem is to find the standard error and then just apply it to your question. That will save you time. So we're going to come here and say standard error. So what is standard error? And we already know our standard error, right? We know our standard error is equal to basically your standard deviation over the square root of your n, right? And so now we have a standard error. So we now have our bottom one. And now that we have this bottom one, we can then solve this really easy. So for this one, we can say that's going to be equal to the x number, right? Minus the mean, right? Divided by what? Standard error, right? So that would give us our z value. To save us time, because these all are all static values that are not going to change, we can put our signs here and here. And so that way we can go ahead and do for this and for this one, right? Why do I think that these numbers are weird? Let me see. I put a dollar sign. I put my parentheses here so that it makes more sense. Yeah, this is what I was thinking. Yeah, the numbers were crazy. Right? Usually when you're solving questions, you want to make sure you put your parentheses, because if you don't do that, Excel sometimes doesn't recognize it. So I usually do, I like to actually overdo. That way I don't have any scenario where I have issues. So this is your Z value. So we now know what our Z values are. So now we now have to find our probabilities, right? And so this is just the same thing we've done in the past. So we'll do norm, distribution, select this value, 0 and 1. And then we'll find for that one, and then we'll find for the second one. Right? So you can see we didn't change anything. This, remember, central limit theory, like I showed you guys prior, it basically works on normal distribution.
Could you click on Z again? Over on it.
And so, like we do the past, right? It'll be this minus this value. And so that's your answer there, right? And we can actually solve that in percentages, right? So to interpret our results, right? We say for sample size of 50, right? The probability that the mean time drivers between the age of 15 to 19 spend driving each day is, between 24.7 and 25.5 minutes is what? 91.21%. All right, any questions on this one? So if you look at this question, right, nothing has really changed other than the Z value. Everything else is just like how we have with the normal distribution. And that's because the only difference here is this. In the normal distribution, we don't have this N value, but we have that when it comes to CLT. And so the Z value is slightly different, right? Other than that, everything else falls in place as it was in normal distribution. And that's why we, in the interpretation, we make sure that we say that it's a size of 50. So anyone who sees this knows that this is not in normal distribution, this is CLT. Right. All right. Any questions?
This is kind of a weird one, but how would you be able to tell that this is like, if you're looking at the question and you didn't have like any of the answers, how would you be able to tell that this is a CLT question and not like just a normal distribution question?
Because in normal distribution, you wouldn't have a sample selection of numbers of 50 drivers.
Got it. Cool. Thank you.
And I will remind you that you said you got it. Right?
Don't hold me to that.
So, okay. All right. Let's try an example. I think sometimes the more examples you try, the more, I got a 2-year-old, so the more examples we try, the more it kind of makes sense for us. So let's try an example and then we'll see if we get this even better. So let's look at this one, right? This one is all about room and board, right? All right, so let's look at this one, right? And let's try to solve this question. All right. It says that the mean room and board expenses per year at a 4-year college, or 4-year colleges, sorry, is 7,540. You randomly select 9 colleges. What is the probability that the mean room and board is what? Less than 7,800. Assume the number that the room and board expenses are what? Normally distributed with a standard deviation of what? 1245. You can see this one also does what? Selects 9 4-year colleges, right? So we know that this is going to be CLT, right? Because we're not looking at the distribution in general, we're looking at specifically at these 9 colleges, right? All right, so for this one, we're going to say that the mean, the population mean we're giving here is 7,540, right? We know that our N is giving us what? 9. We also know that our X is giving us less than what? 2,800. And our standard deviation is giving us 1,245. All right. Questions so far? We can even draw this, right? So I'm going to go ahead and do that. We can even draw this. For me, drawing, and I know maybe because I'm old, but when I draw, I tend to see it better. So the mean is 740. And so, and we're looking at the X is giving us 7,800, but we're told it's less than. So since it's less than, I know that I'm going to shade this way, right? Shading this way. For my Z value, this is 0. I don't know what this is. All right. And so I'm going to have to find this, and then find this. Or in this case, I already know this one, so I'm going to find Z. So for this question, it's straightforward, right? Before I start, I'm going to try and find my standard error, because for me, it just makes it easy for me, right? So my standard error is equal to what? My standard deviation divided by what? The square root of 9, right? And so I get that as 415. Now that I have the standard error, I can then go ahead and find my Z value, right? And my Z value is giving as my X minus my mean divided by what? My standard error. And so I get 0.626506, right? The question is asking us to find the probability of what? Less than what? 7,800, right? And to do so, it's going to be equal to norm disk, this value, 0, 1, true. So we get our answer as that. Questions? I don't know if I'm moving too fast. So if I'm moving too fast, ask me questions. You can ask, you can type publicly or privately, right? That way I can see what you're saying and I can respond to you. Okay. Could you hover over standard error? Okay. This one, right? Okay. So that's standard deviation over the square root of n. Cool. All right. So now we can interpret, right? We can say it's with the sample size of 9, but normally distributed, the mean, the probability of that the mean, room and board is less than 7,800 is 73.45%. All right, any questions on this one? All right, looks like we got this all down and we're good on that. That's good. All right, let's look at, so what we've done here is that we've gone through CLT and we're finish on CLT now. So now we're going to look at another topic, right? Because we're done with CLT for now. And we kind of explained CLT. I did a couple of examples. We did about 4 examples on CLT. So you all understand what CLT is, right? And so now we're going to look at another topic. And that topic is called normal approximation to binomial distribution. So let me share my screen. All right. So I want to explain this first before we solve it. I want to explain what that means, right? So one simple way to look at it is, when we did binomial, right, we didn't tell you the limit, but usually binomial is only used for a small set of numbers. Usually when you have less than 30 numbers, we use binomial distribution, right, where we do x, n, p, and then false or true. When we have larger numbers, especially when numbers are more than 30, we don't use binomial distribution formula to solve it. We use normal distribution to solve it. And that is because normal distribution is made to basically work with large numbers. Binomial is, remember, binomial, the whole concept of binomial is 2 options, true or false, and it's used for like coins or used for small scenarios. Normal distribution is different. It's used for large numbers. So whenever we are faced with a big number involving binomial, we actually use normal distribution to help us solve it. So the rule of thumb usually is 30, right? So we tend to use normal distribution to help us solve these binomial questions, right? So that's why we say normal approximations. So that means we're using normal distribution, right, to help us solve binomial, right? But we're using approximation because in theory, normal distribution is a continuous probability. And so the values are never exact. We will try though to make it as exact as possible because binomial is what? A discrete probability. So we're going to try to do that. And I'll get to that very soon. So there are a couple of steps that we have to follow to be able to do this, right? It's like a 5-step process to be able to take binomial distribution and approximate it using normal distribution, right? And so, but before that, I just want to list some of these examples. So let me see. So here's the examples, the steps to follow to do that. We're going to go through these steps to solve all our questions. That way you won't have any problem understanding what these steps are. So let me copy this because we're going to use them. So here's the first step. Before you solve any question involving binomial, normal distribution approximation of a binomial question, you have to state what n is, which you all know, right? N is the number of trials, right? P is the probability of success. Q is the probability of failure. That's the first step. The second step is you can only approximate a binomial distribution if your mean is at least 5, right? So that's one of the theories they have to follow. So this is very important. So n times p has to be at least 5, and also n times q has to be at least 5. All right. Now, if we don't have the tools to kind of show you, right? But if you look at it, right, when n and p is less than 5, it doesn't form normal distribution. It only forms normal distribution when you have 5 or more. That's why we do that, right? So if it doesn't form a normal distribution, then we cannot use it to solve anyways. That's why this is a very important concept. And the third one is we have to find the standard deviation and the mean, right? Then here's the fourth one. This is an important one that I want you guys to pay attention here. So if you're sleepy, wake up. This is very important. This is called continuity correction. Let me explain that before we go on. So what is continuity correction? Now remember, right? A binomial distribution is a discrete value. That's why, if you remember, in binomial, we had exactly 4. And when you said exactly 4, you just went and said x was 4, right? And then you put 4, and then you put true or false. That doesn't happen in normal distribution. If you remember, in normal distribution, we always use what? True. Because in normal distribution, we don't have an exact value, right? Because we're approximating, so we don't have an exact value. This will help you understand this better. So when we have, like if you have a histogram, all right? If you are calculating a histogram, right? If it's in the term, if it's a binomial, if you have this value here, right? This value here, C, right? You will say the probability of C, right? Because C is the exact value. Now, that doesn't hold true when you're doing for normal distribution. In normal distribution, if you say C here, it's not true because yes, you're assuming that it's C there, right? You're saying probably C there. So in order to turn a normal distribution into binomial, what we do is we do what we call correction. And to correct that is we'll say, okay, if you're looking for exactly C here, we have to subtract 0.5 here and also add 0.5 here. Because when we do that, right? When we do that, then we'll end up getting an almost exact value. Because when we have that number, we know that it might be shifted a little bit right or left. We don't know. But to correct that and to make sure that that value looks like an exact value for binomial, we'll subtract 0.5 to the left and then we'll add 0.5 to the right. That way we get an exact value. That's how we we are able to correct a normal distribution to look like what? A binomial distribution. And it's called continuity what? Correction. Any questions on that? Let me do a couple of examples of that, so that just to make sure that you all get it, right? So let's do a couple of examples so that you understand what continuity correction means. So let's try an example. Let's say probability of getting between 250 and 300, both inclusive, right? So in this example, right, we're looking for between 250 and 300, right? If that's the question that we're giving in binomial. So if we're going to solve that in normal distribution, since 250 and 300 are inclusive, the best way to solve that to get a result that is almost correct will be to subtract 0.5 to the left side and to add 0.5 to what? The right side. That way we correct any errors that might happen, right? And so what we would do there, we now say, okay, this is going to be 249.5, right? And 300.5. By subtracting 0.5 to the left and adding 0.5 to the right, we'll correct any errors that might be in that calculation. Any questions on that? Okay, let's try another example. I'm going to do like about 3 or 4 examples before we move on. Let's say we're finding the probability of at least 130 successes, right? Now, at least 130, right? Who can tell me what the lowest possible number is for at least 130? Anyone? Your here said 0. Now, think about it again. If you have at least 120 success, what are 30 successes or success? What is the lowest possible number there? All right. So it's going to be 130, right? So to take it, well, 0.5 will be, that's correct. Good job. So here, right, you're going to say the x, that's correct. Good job. So you're going to say your x is greater than what? 129.5, right? Because the lowest possible number is 130, right? So then you take away 1.5, 0.5 for the other side. Now, what about if it says probability of, let's see, of fewer than 75? What would x be? Anyone? If it says fewer than 75, what would be the correction? What would be the correction? All right, nice, right? That correction there would be 74.5. Nice. What about probability of, which one is left? At most 44 successes. What would that be? right? At most 44 means that the top post is 44, right? So in that case, you're going to do 44.5, right? And then the last one, what if it says probability of exactly 100, right? What would be the value there? Right, since this is exactly 100, that would be what? 99.5, right? And 100.5, right? That's how we do course correction, basically, if you're given a question. So this is very important because when we correct it like that, then we can now solve for the value and get our answer for that question, right? All right. Once we get that, right, the next step is just to find our z value, which is just your x minus your mean over standard deviation, and then find a probability, right? So those are the 6 steps that you follow to solve questions where they ask you to approximate a binomial distribution using the normal distribution. So we're going to do a few examples here so that you guys will feel comfortable with this, and then we'll give you some question to do extra credit. I mean, group work, and then we'll do extra credit, and then we're out of this place. Right. So let's try a couple of examples. So we're going to go into Excel and try some examples. All right. All right. So look at this first example, right? So we're looking at example 1 on that normal approximation to binomial distribution. So look at this example here. So this first one says 62% of adults in the US have an HD TV in their home. You randomly select 45 adults in the US and ask them if they have HD TV in their homes, right? So looking at this question, let me see if I can enlarge this, right? So we're going to look at this question and we're going to try and see how we can solve that. All right. Let's see. Okay. All right. Look at this question. Now, based on this question, you can see we're told that 62% of adults in the US have HD TV. You randomly select 45 adults in the US and ask them if they have HD TV. So let's solve the things we know. Here we know that our n will be equal to what? 45, right? We know our p is given as 0.62, right? And if we do that, then we know our q is equal to 1 minus this, and that's equal to 0.38, right? That's the first step. Let me see if I can, do I still have that? Okay, I have that, good. So this is the first step, right? The first step says you should find your n, p, and q. We did that. The second step that says, is np and nq greater or equal to 5? So we're going to do that. So np will be equal to 45 multiplied by this. That gives us 27. Then our nq will be equal to this multiplied by this. So you can see this passed the second test, right? That's the second test. Pass the second test. Right. The third test says you should find the mean and the standard deviation. So we can find the mean. And that's not difficult, right? Because the mean is already this. N times P is the mean. If you remember when we did binomial, we said N times P stands for the mean. Next one is saying we find the standard deviation. That's also easy because the standard deviation from binomial was what? The square root of N times P times Q. It's easy. So we do the square root. And we do N. times P times Q. And that gives us that, right? Now, this question is not complete, obviously. It's just to kind of help you know how to set up your steps. So this way we have set up our 3 steps, right? But we weren't given to find anything. So we can't do the 4th step or the 5th step or the 6th step. But at least this helps you understand how to do your 1st, 2nd, and your 3rd steps. Right? Same thing with this one. We can try this one too, because this one also is going to show you some of the basic things to look for. Right? Here it says 12% of adults in the US who do not have HDTV in their homes are planning to purchase one in the next 2 years. You randomly select 30 people who do not have HDTV and plan to use them to purchase one in the next 2 years. Now, in your exam, I'm going to use normal approximation of binomial distribution. I'll add it here so that you know what to do to solve a question like this. So that will not be a problem in the exam. All right. So for this one, right, let's also do the first. Let's try and find out what our N, P, and Q is. Right? So let's do that, right? So Samuel, what's our N here?
Is it 30?
All right. What is our P?
2? Oh no, 0.12.
0.12. Okay. What's our Q?
Is it 2?
That'll be 1 minus our P, right?
Oh, okay.
That gives us that. And that's so we got our first one. So let's do the second step. So the step is N times P. So we're going to come here and say N times P. And that's equal to N times P. And then for the second one is NQ. And then for the second one, NQ. And that's N times Q. Now, what is wrong with this? Is there anything wrong here?
N and P are less than 5.
Yes. So we cannot use normal approximation of this binomial distribution since mean is less than 5. So you can see that we were not able to solve this question because it went above, it didn't meet our second rule, which says that N times P and N times Q should be equal to 5. So that means we can't solve. We have to stop here for this one. I hope this makes sense. All right. Let's try 2 more examples just to make sure that we understand. So let's look at one that we can address from the beginning to the end. Here we're told that 58% of adults say they never wear a helmet when riding a bicycle. You randomly select 200 adults in the US and ask them if they wear a helmet while riding a bicycle. What is the probability that at least 120 will say they never wear a helmet riding a bicycle? Right? So let's look at this one. All right. So Reese, what's N here?
N would be 200.
Okay. What's P?
0.58.
All right. What's Q?
It's going to be 1 minus 0.58, which is 1.42 or 0.42.
Man, look at you on the roll. All right. So we got the first one, right? So we got the first step all done, right? So now we'll do the second step, right? So for the second step, we're going to see if it meets that. So it's going to be N times P, right? So that'll be equal to this multiplied by this. And then NQ is going to be this multiplied by this way. Do we have a problem here?
No.
Good. So we are good and dandy here. And so you can see that we are able to show clearly that we've met the steps. So we now have to do step 3, right? And so in step 3, what we're going to try and do is to try and show the mean. And we know that the mean here is the same thing as n times p, so we know the mean here. And standard deviation here is basically the square root, right, of n times p times q, and that gives us the square root. So we've done the 3 steps, right? We can even draw this if we want to, because we know now that the mean is what? 116. So we know that, right? That's a normal, this is a binomial question, but you can actually show it in normal distribution here, right? Okay, now let's do step 4. Step 4 says continuity correction, right? So we're going to try and correct this. So who can tell us how we can correct this? So what would the value be? It says that it's at least 120. So what would be the correction here? Anyone? 119.5, thank you. That's correct. So that's 119.5. And so for here, we'll do the same thing, right? 119.5. This is at least. So we're correcting that when we're doing this, right? And so once we do that, right, we can now find our z value, right? Because now that we've corrected that, we can then go ahead and find our z value. So our z value will now be equal to, right, our x value minus our mean, right? And we can even do standardize here. That would save us time, right? So we'll do standardize. And we're going to find our x value. And we're going to find our mean and our standard deviation here. And so we get 0.5014. So we got this, right? I don't think I'm going to call off for that. And so the probability will be, right, the probability here will now be equal to norm disk, right, z value 0, 1, 2. But you can see that the question here is to the right. So we have to do what? 1 minus. So our answer here will be 0.38. Right? So the probability that at least 120 adults will say they never wear helmets when riding bicycle is 30.80%. Right? And we can do that by fixing that. All right. So you can see that we are able to find the answer for that question using all the steps that we are required to provide. Any questions on that? All right. Let's do one last one before I allow you to do some classwork. So look at this question. This one says a survey reports that 62% of internet users use Windows 10 as their browser. You randomly select 150 internet users and ask them whether they use Windows 10 as their browser. What is the probability that exactly 96 will say what? Yes. Right? So same thing here, right? I can go here and I can go and paste this again. Right? And we can go step by step with this one too. Right? Our N here is 150, right? Our P is given as 0.62. And our Q is given as 1 minus this, which is that. Right? And then we can find NP, the second step, right? So N times P, then NQ, we can do that equal to N times Q. So we're fine, right? In both instances here, none of them is less than 5. So we're fine on the second step. So now the third step is to find the mean. And we know that the mean here is going to be 93. And then to find the standard deviation, it's basically going to be square root of N times P times Q. All right. Continuity correction. Who can tell us the answer for this one? Here we're told it's exactly 96. So how do we correct that? Anyone?
Are you gonna minus 0.5 and also add 0.5 to 96?
Exactly. So that would be 95.5 and what? 96.5, basically. So basically what you have here is a scenario where you have a mean of 93, and then you have 95.5 and then 96.5. And so to correct that, this is it. Right? That's how we correct that. Your X values, Z values. So to do that, what we're going to do basically is we'll now say, okay, let's find the Z values of that. All right, and so that's easy, right? We do standardize. All right. We do X, comma, mean, comma, standard deviation. All right. To save us time, it's going to do this, and I want to do this. Press enter, and I do that. Now we find the probability. So it's like you're finding for two values, like how we do when we're finding for two values. That's how you're going to do this one. Right? Non-disk, you're going to do 0, 1, true. Right? And remember, right, we just subtract. That's it. We're done. Right? So probability that exactly 96 will say they use Windows is 5.93%. That's it. Any questions on that? All right. Testing time. Let's now see if you have been paying attention and you've been following the class. We'll now see if you guys can do that. So I'm gonna, it's just three of you. I'll put you guys in one group. And I'm gonna have you guys try a question, and we'll see basically if you're able to do that, right? I'm confident that you're gonna do it anyways. So I'm just, well, I'm gonna try and see you guys work on that question. So I'm gonna have you guys try. Let me see if I give you, let's go to time. So you got some time. When we come back, we'll just talk a little bit about that, then give you extra credit questions, and I will be out of this place. But I want you guys to try question 6, right? Education finance. So there's A and there's B and C. So I want you guys to try that as a group. Somebody open your Excel, and then the rest of you can kind of be working together to solve that question, right? And so, any questions before we do that? All right. I'll see you guys in a few. All right, welcome back. So it looks like you guys were able to get that question done. That's good. So usually that question kind of gives students, sometimes it gives students concern on how to solve it. And one of the things you just need to remember is this is a question that it tests to see if you understand the difference between what we did today to what we did a couple of weeks ago or a week ago, right? So if you look at the question, what you will see is that this first one is your normal, it's just a normal distribution question, right? And then this one is CLT. That's the difference, right? And that's why this one covers general terms. This one is from, the result is going to be from a select number, which is 25. So that's the key difference between the two of them. So for your extra credit, you need to do 4 questions. Well, 3, because you already solved this one. So your question will be 5 and 6. All right, 5 and 6, and 5 and 6. So 5 and 6, sales price of a single family, education corporation, and then 5 and 6, this one and this. And that would be extra credit for this week. Any questions before we go? All right. Looks like there are no questions. I want to thank you all for being here. And if you have any questions, you can stay and ask. If not, you all have a good evening, and I'll see you guys. Don't forget your discussion post is due tomorrow on the one distribution. It's a couple of videos to watch, really good videos to watch and respond about the one distribution for this week. So don't forget to do that by tomorrow so that you get a chance at full credit. All right, other than that, have a good evening, and I'll see you guys either at the discussion tomorrow or next week.
Thank you, Professor.
Bye.